Today I am just going to give a very brief introduction to what is entropy, what is mutual information, and some properties of entropy and mutual information. Now if you are wondering what relation does this have to this course, so there are some results in regenerative codes which can be proved using information theoretic methods basically. So you will need some knowledge about entropy, mutual information, chain rule for entropy or mutual information, and some simple properties of entropy to prove those results. And Uday is going to cover one such lecture on day 8. So that's why we thought we will just give a very brief introduction on entropy and mutual information. So my outline of the talk is like this. So first I will talk about how can we quantify information. So I'll talk about measures of information. Then I'll define what is entropy, conditional entropy, relative entropy, or after that I'm going to talk about what is known as information theory inequality. This is a result basically which we are going to use to prove many properties of entropy and conditional entropy and mutual information. And then we will go into properties of entropy and chain rule for entropy and mutual information. So this is the plan for today. So let's start with the first topic, which is measure of information. So how do we quantify information? So what is information? So let's say I'm saying Udaya is from University of Melbourne. Does this convey information to you? I say it does not convey any information. Why? Huh? We already knew that. There's nothing, it is a known fact that Uday is from University of Melbourne, right? So there is no information in my statement that Uday is from University of Melbourne, right? But if I say there's a 40% chance of having a rain tomorrow, does it have information? It does, because I don't know whether it's going to rain or it's not going to. If I say there's a 100% chance of rain tomorrow, then again that's a known, because that's a known fact, it's going to rain. But now I said the 40% chance of having rain. So that means it has, I don't know, it may rain, it may not rain. Okay. Now which has more information? If I say there is 90% chance of rain tomorrow, that is statement 1, and I say there's a 50% chance of rain tomorrow. Okay, you are right, 50% is more. Why? Because if I say 90% chance, then you are almost sure it's most likely it's going to rain. So that's not, but if I say 50%, you don't know that it's going to rain or it's not, right? So basically Shannon considered something which has uncertainty has information, right? So we are trying to quantify information. So the first person who tried to quantify information was Hartley. Now you may have seen Hartley somewhere else. Hartley's oscillator, exactly. He's unfortunately not known for his information theory, this thing, but he's known for his oscillator. But Hartley was the first person in late 1920s, and he said if you have a random variable x, it has L different possibilities, then he said the information content is log of L to some base b. So he recognized that if there are more possibility of a particular random variable, more information content it has. So something which has only 2 possibility has less information than something which has, let's say, 100 possibility. He was right to decipher that. However, this measure of information is also not correct. There is a problem with this measure of information. Can you tell me what is the problem with this measure of information? So he says basically if a random variable x has L different possibility, information content is log of L. What is the problem with this measure of information?
All possible values are equally likely to happen.
Exactly. So consider again 2 cases. I have, okay, let's consider balls. I have a red ball and a blue ball, right? In one case I say in a bag, I have 90% probability of getting, if I pick a ball from a bag, 90% probability is getting a blue ball and 10% probability of getting a red ball. Second case, I have 50% probability of getting either a blue ball or a red ball. Now, according to Hartley's measure information, in both the cases there are two possibilities, red ball and blue ball. So, according to his definition of measure information, both these bags, when I do this experiment, both these experiments have the same information, but you clearly know that if a ball has 90% probability of getting a blue ball, I know for most of the time I will get a blue ball. So, that has less information. So, clearly, as you rightly pointed out, he did not, it does not take into account the likelihood of occurrence of that particular event. He just considered, okay, there are n possibilities, so log of n, but he did not consider, okay, these n possibilities with what probability they are happening. So, Shannon was the person who actually recognized that. So, he gave this measure. So, if say if the ith possible value of x has probability pi, then Hartley's information should be weighted by the probability of occurrence. So, he said this is information provided by x, and this is what is Shannon's measure of information. Yes, Shyam.
What's the point of using log?
What's the point of using log? Okay, I will give a simple example. So, why is log a good measure of information? In fact, I'll give a simple example to illustrate this. I'm not going to proof of why log is a good measure, so I'm just giving an example. Yeah. So, there is a measure of information to satisfy some axioms. So, from that you can show basically the form of the information measure should have the form of this entropy only. Okay. Now, I'm just again go back to my example of blue ball and red ball. Okay. Now, I'm doing an experiment and I'm picking up a ball from a bag, and I want to convey to you what color ball I picked. Okay. So, in this case I have two balls, red balls and blue balls, right? Correct. Now, can you tell me how many bits I will require to code this information? I have only two possibilities. So, I can just use, and let us consider I am using a binary code, correct, 0 and 1. So, I can do with 0 and 1, right. So, I had two possibilities. Essentially, I am using log to the base 2 of 2 number of bits to represent the information. Similarly, consider, let us say I have 4 different color balls, and again I am doing this experiment that I am picking up a ball and I want to disclose the color of that. So, I can using 2 bits I can represent the information. So, I am just through an example I am just illustrating that log is the measure to illustrate, because essentially if you look at, I had 4 in this case 2 raised to the power 2, and I am using log to the base 2 of 2 raised to the power 2. I am using 2 bits to denote that. I didn't mention the unit. Initial first slide I mentioned the base b. Typically we use base 2 and the units is bits. Okay. Now, that's the most commonly used this thing. If the unit is e, natural, then if we are doing natural log, then it's called nats, and if the unit is 10, which we never use, it's called Hartley. So, it's a very dubious distinction they are given to Hartley. I mean, we almost never use base 2. Then, in fact, by default we use base 2, basically bits. Okay. So, I hope that kind of answers, but there is a rigorous proof of why measure information should be of the form of summation minus p log p, this thing. Robert Ash book has this proof. You can have a look at it, or I'll show you the proof I have in my, not in this slide, but I have in my information theory lecture slides. For okay, yeah. So let me define. So if f is a real value function, then I define the support of f to be the subset of its domain where f takes a non-zero value. So and I represent the support of this function f by this. So the uncertainty or the entropy of a discrete random variable x is given by this expression, and this is defined over the supports of set of this p of x, because we are taking log of this. So p of x has to be basically greater than 0. Okay, so or in other words, I can write it. I write this as expected value of minus log of p of x. So that's your entropy function. Similarly, I can define a joint entropy function. So if you have random variable, discrete random variable x and y, then joint entropy function is defined as expectation of minus log of joint distribution of x and y. So this is basically given by this expression. This is joint entropy function. Just take an example. Let's say x takes two values, x1 and x2, and probability of x1 is p and probability of x2 is 1 minus p. Then the uncertainty or the entropy of x is given by this expression, minus p log p minus 1 minus p log of 1 minus p. And this function has a special name. It's called binary entropy function. Now some books use the notation small hp to denote binary entropy function. I just avoid that, because when we talk about continuous random variable, we have a similar notion like this. This is for discrete random variable. Similarly, for continuous random variable, we define what is known as differential entropy, and for that we use the notation small h of p. But in many books you will see they, for this binary entropy function, they also use the small h of p. And this looks like this. This is, I have plotted binary entropy function as a function of this probability p. Maximum value is 0.5. At 0.5 is 1, and it's 0 at these two, at p equal to 0 and 1. Okay. Now we are going to prove a result which is known as IT inequality, and this is quite useful to prove some of the results, properties of entropy and things like that. So for a positive real number r, log of r is less than equal to r minus 1 log of e. I mean, just if I just plot let's say if I plot the natural, if I plot this, how does it look like? Huh? Something like this, right? At r, once again, at r equal to 1, or I can, basically it will be something like that. And how will r minus 1 look like? R minus 1? Huh? It will pass through? It will be this thing. And we are going to prove that this, now if I multiply both sides by log of e, I will get this expression, change of base. Instead of a natural log of r, I will get log r is less than r minus 1 log of e. So this I will prove by showing that of course they meet at one point and at r equal to 1, and below this its slope is something, and after this the slope is something. So that means this function log of r lies below this line r minus 1. And if you notice in our expressions of entropy, we are getting log, okay, we are getting this log. So log of r, so whenever we have to simplify some expression, we will use this IT inequality. Log of r will be upper bounded by r minus 1, and we will use this result to prove some properties of entropy and divergence and things like that. I will come to that. So this is a quite useful inequality, and it's equal at r equal to 1. So the graph of log of r and r minus 1 coincide at r equal to 1, and if you look at the slope, 1 minus r is basically greater than 1 for r less than 1, and it is less than 1 for r greater than 1. So these graphs do not cross, they meet at r equal to 1, and below that the slope is greater than 1, and after that the slope is less than 1. So basically this line log of r lies below r minus 1. So this is the proof of this. You can prove it multiple ways. You can also again form a function r minus 1 minus log r and differentiate it, and I can show it. This is just one way of proving it. And again, many of these results in information theory can be proved in multiple different ways. Okay. So just remember this result, because as I said, whenever we get entropy kind of term where we have log of probability term, we are going to use this upper bound to simplify our results. This is known as IT inequality. Okay. And of course, if I multiply by log of E, I get this desired form. Okay. Now let's look at some of the properties of entropy. So if x is a discrete random variable which takes L different values, then you can show that entropy is lower bounded by 0 and upper bounded by log of L. And equality on the left hand side happens if p of x is 1 for some x, and for all other basically x it's basically 0, and on equality on the right hand side happens if x is uniformly distributed. So let's recall the definition of entropy. This was this sum over the support of p of x. So let's look at minus px log px. Now for the case px is 1, the log of 1, that will be 0. So this is 0, and for all other values of p of x which lies between 0 and 1. So if this lies between 0 and 1, log of this will be a fraction, right? And log of fraction will be a negative quantity. So negative multiplied by negative, that will be positive, and p of x is a number, positive number. So then this quantity will be positive. So basically what we have shown is then h of x is basically going to be greater than or equal to 0. And this will be 0 only if this is equals to x for every x belongs to the, and there can be only one such x. Now let us prove the upper bound. And what was the upper bound? That h of x is less than or equal to log of L. So the first step, we replace this by the definition of entropy. So I am writing this as minus summation over the support of p of x, px log of px, and then minus log L. Now minus log of L, I can write this as, now summation, sum of probabilities will add up to basically overall x belong to support group of p of x. This will add up to 1. So what I did was, here I can just multiply it by summation of p of x, x over the support group of p of x. If I do that and then I take this as common, what I get is minus log of p of x. So minus log of p of x is log of 1 by p of x. So that's this, and this will be minus log of L, because this is already taken out. Correct? Now minus log of L, it can be plus log of 1 by L, correct? And then you have log A plus log B, that is, so this will become log of 1 by L times p of x, correct? So now I have this expression. Okay. Now this is of the form log of r. So this using IT inequality, I can upper bound it by r minus 1. So log of r is r minus 1 log of e. So I did like this, and now basically, so p of x is 1 by L minus summation of p of x. So this x takes L different values. So when I sum over all x, this can be basically written as 1 minus, and this summation of p of x 1 minus 1 log of e. So that's 0. So what I have shown you is h of x minus log of L is less than equal to 0. And where is this equality thing coming up? Log r, exactly, r equal to 1, because here I am using log of r is less than equal to r minus 1. So r is 1, meaning 1 by L px is 1. So px is 1 by L. So basically it shows, so this basically proves that h of x is equal to log L when it's uniformly distributed. And that's what the examples that I gave, like when I said 50% probability of getting blue ball and red ball, that has more information than the case when probabilities were 90% and 10%. Okay. There are other properties also. I mean, I am just writing. So this is a change of base. If I compute entropy to the base b and compute entropy to the base a, they are related in this particular way. Again, I can write log of p to the base b as log p to the base a into log a to the base b, and then this entropy will be minus p log b, p summation over the support set of this p. So this is, so if I sum over this, I can take log b to the base a, because it doesn't depend on p of x, and take it out. So what I get is this, and this is nothing but entropy to the base a. So I get this relation. Similarly, I can define, I defined entropy, I have defined joint entropy, I can similarly define conditional entropy. So conditional entropy of the discrete random variable x given a particular event y equal to v occurs is given by this expression. So this is basically conditional distribution of x given y log of conditional distribution of x given y minus and sum over the support group of this joint distribution function. Now this is different from this. What is this? This is the conditional entropy of a random variable x given random variable y. And what is this? This is given a particular event y. Let's say y is some event, it can have multiple possibilities, like let's say I am talking about tossing of coin. So y is either y is head or y is tail, right? So when I compute this conditional entropy, I mean, and x is some other random variable, then this is condition on y. Whereas if I say condition on whether I say, okay, head has happened, then what happens to x? That would be this. Okay, and we can find out this conditional entropy of x given y by basically scaling this conditional entropy given a particular event by the probability of that particular event. Okay, so for example, if x is a random variable and I said y is a random variable, which is basically we say y is either head or y is tail. If I ask you to find the conditional entropy of x given y, then you first find the conditional entropy of x given y is head and find out conditional entropy of x given y is tail, and then you multiply this by probability of occurrence of head and you multiply that by probability of occurrence of tail. What you will get is this. Okay, or if I want to write this in terms of this, it would be minus summation joint distribution of x and y, because p of y multiplied by p of x given y. So that would be joint distribution of x and y log of p of x given y. Okay. This is slightly confusing in a sense, like people make a mistake here when you ask them conditioned on an event and conditioned on this random variable. And conditioning typically cannot increase entropy. So h of x, because you can think of it like, okay, event y has happened and then you are seeing what is the effect of y on x. So h of x given y is always less than equal to h of x. However, given a particular event, we cannot say that, it can be either way. But h of x given y is always less than h of x. So conditioning cannot increase entropy. Now I am defining what is known as relative entropy. There are multiple names for it. You also call it divergence. So divergence between two, so it's a measure of closeness between two distributions. So if x and x hat are two discrete random variables with same set of possible values, then information divergence or relative entropy is defined like this. So it's the expected value of basically log of p of x divided by p of x hat x, where the expectation is taken with respect to x. Just give an example. So suppose x is a random variable that has L possible values, and let us say x hat has uniform distribution. If I ask you to find divergence between p of x and p of x hat, this is the expected value of log of p of x given p of x hat, and expectation is with respect to p of x. So this is uniform distributed, so I can write it as 1 by L. So this becomes, now this will, I can make L go here. So expected value of log of L will be log of L minus plus expected value of log of p of x, which I can write as minus expected value of minus this, and this is basically entropy function. Now what I have shown you? I have shown you h of x is less than equal to log L. So from here, can you comment on this? What is the value of divergence when both x and x hat have same distribution? Because here in this case x hat was 1 by L. If x also has same distribution, then this divergence will be. So it's a measure of, it's actually a measure of closeness between two distributions. So two distributions are same, divergence will be 0. But if they in this particular example, I just took x hat to be a uniform distribution. Okay. I just wanted to prove a result on divergence, and divergence is greater than or equal to 0. I just proved it using whatever result I already have shown you. I can also prove this from first principle if I don't want to use this. So what was divergence? It's the expected value of log of p of x by q of x. So I took minus of divergence. So this became then log of q of x by p of x. Okay. Now again log of r, I use IT inequality. So this will be less than or equal to r minus 1, and then you sum it over this. The support group of this p and q are same, because if you remember how we defined it, we said x and y discrete random variable with same set of possible values. Okay. So when I sum them over q, this is 1 minus 1 log of p. So I have shown minus of divergence is less than equal to 0, or divergence is greater than 0. And you can see from here when r is 1, divergence will be 0. So which is basically saying q of x and p of x have the same distribution. Now this is a very, very important property, and which is very extensively used, which is called chain rule. So if I have a joint entropy of x1, x2, x3, xn, I can write it in terms of conditional entropy. Okay. So for example, if I have h of x1, x2, I can write it h of x1 plus h of x2 given x1. Okay. And I just use this property that if I have this joint distribution, I can write it in terms of this conditional distribution, correct? So if I, so for example, joint distribution of x1, x2, I can write it as x1 into x2 given x1, right? So this is basically, so in general for joint distribution x1, x2, xn, this can be written like this. Now, if you do that, now from the definition of joint entropy, this is basically the expectation value of minus log of this. Now this thing can be written as this. Now I am taking log of product terms. So what is going to happen? I am going to get sum. So I am getting this sum, and then these are expectation of minus log of conditional probability, which is basically my definition of this conditional entropy. So you can write this as like this. Now this has been used in variety of ways. Like example, if I have h of x1, x2, x3, I can apply chain rule in multiple ways. I can write h of x1 plus h of x2 given x1 plus h of x3 given x1, x2. I can write the same thing as h of x3 plus h of x2 given x3 plus h of x1 given x2, x3. So this chain rule can be applied in multiple ways, and it's a very useful thing used in to proving lot of properties of this. Now lastly, I am going to define what is a mutual information. I will come to the name in a little bit. First, let us look at the definition of this. Why it's called mutual information? Once I derive it, I will come to that. So if you look at mutual information between two random variables x and y, they are essentially defined as diverges between the joint distribution of x and y and the marginal distributions. So mutual information by definition is given by this. Okay. Now what I am doing is I am writing this joint distribution between x and y. I can write it as p of y into p of x given y, right? And then I get rid of p of y, which is there in the numerator and denominator. I get this. Now, so then look at this term, summation of pxy log of 1 by px, which is this term plus this term, the numerator term, correct? Now the numerator term I can write as minus minus of, this is summation over x and y, joint distribution of xy log of p of x. What is this? Does this depend on y? No. So if I sum this over y, what are you going to get? P of x, right? So what I will get is this, and this is a known form. What is this? Conditional entropy of x given y. So what I have shown is the mutual information between x and y is given by uncertainty in x minus uncertainty in x given y. So what is this is uncertainty in x, and this is uncertainty in x having known y. So difference is whatever information y is giving about x, because earlier your uncertainty in x was h of x. Now that you know y, your uncertainty is h of x given y. So if you subtract that, that is the information y is telling about x, correct? Now, yeah.
What's the relation between this h and I?
H and I. So
Here in the left hand side we are using the symbol I. So in the Hartley major equation we use the term I.
Oh, okay. So maybe I should have been consistent with this. I think what I did was no, this is not mutual information. This I just, for information I just used information of x, I use I of x. Okay. So this may not be a standard notation, in the sense like we use for mutual information we use I of mutual information x and y, we use this notation. Okay. So this was I just used to denote information content of x. Okay.
Does it mean that h is equal to minus I, it would be, because more uncertainty means less information?
No. So this is a relation between mutual information and this. So
See, sir, here also we are not using minus sign here.
where minus sign?
Mutual entropy, we are using this.
No. This is
Mortality ratio kind of the thing.
no. I am saying mutual information by definition is this. It is a divergence between joint distribution and marginal distribution. I can write mutual information. In fact, I might have it later on. Just a second. Mutual information is written as divergence between joint distribution and marginal distribution. Now, how did we define divergence? If you go back, we define divergence as, so divergence between P of x and P of x hat is, it is expectation of log of P of x and P of x hat, and this expectation is with respect to this. Okay. Now look at mutual information. This is divergence between this and this. This expectation with respect to this joint distribution log of, so this is your x and this is your x hat, P of x and P of x hat, and this is P of x. Okay. So this is the definition of mutual information. Mutual information is defined as divergence between the joint distribution and marginal distributions. Okay. So joint distribution between x and y, and divergence with that of marginal distribution of x and marginal distribution of y. This first line is by definition of mutual information. Now what I am showing is, I can write mutual information in terms of entropy of x and y. And what I have shown you is that this mutual information can be written as entropy of x minus conditional entropy of x given y. And what I am saying is, now if you look at this, what does this intuitively mean? H of x is the information content in x or uncertainty in x. What is h of x given y? This is uncertainty in x given that you know y. So if you subtract that from h of x, it means earlier, so when you had known earlier the uncertainty in x was h of x, now that you know y, this is uncertainty. So if you subtract it, that much information is conveyed by y about x. Now I am going to show you whatever information y conveys about x, it is the same information conveyed by x about y. So I am going to show you the next slide that mutual information can also be written as h of y minus h of y given x, and hence the name mutual information. Like what information x is given about y, the same information y is giving about x. So the point I am trying to make here is, the way I proved it, I showed that mutual information is h of x given h of x given y. So is essentially the reduction in uncertainty as a result of knowing y. Okay. Now I made a statement that h of x given y is less than equal to h of x some time back. Can you prove it with whatever we have so far? Whatever results I have shown so far, can you prove that h of x given y is less than equal to h of x? First thing we can prove it by showing mutual information is greater than equal to 0. Now how can we prove that? You can use IT inequality, or I just said mutual information is divergence between joint distribution and marginals, and I just proved that divergence is always, greater than equal to 0. So that means mutual information is greater than equal to 0. So that proves h of x is greater than equal to h of x given y. Now When is mutual information 0? When y is not providing any information about x, then of course there would be no reduction in uncertainty. Okay, so I have shown you this, right? Now I am going to show you mutual information can be written also as h of y minus h of y given x. That means entropy of y minus conditional entropy of y given x. So to prove that, I am going to invoke, what did I invoke? Chain rule, right? This is h of x1, x2. So this x and y can be written as uncertainty in x plus uncertainty in y given x. This I can also write as uncertainty in y plus uncertainty in x given y. The same quantity, I just wrote it differently. So these two are equal. If I equate them and I move this to the left hand side, move this to right hand side, I get this, I get this. So what I have shown then, whatever information y conveys about x, the same information x is also conveys about y, and that is why the name mutual information. Okay. It is a very useful quantity because we define capacity and other things basically based on this mutual information. I have already proved this, so I can skip this. Therefore, any two discrete random variable x and y, uncertainty in x given y is less than uncertainty in x, and this happens with equality if they are independent. If I look at mutual information, this is given by this quantity, and mutual information is also given by divergence of this joint distribution and the marginals, and divergence is greater than equal to 0. So this has to be greater than equal to 0. Okay. And we know divergence is equal to 0 when this is equal to this, and that is a condition for independence. Now we can also similarly define chain rule for mutual information and divergence. I will just state it. So mutual information between x1, x2, x3, xn and y can be written in this particular form. So how do I get this? So mutual information I can write, so think of mutual information between, let's look at this is x and this is, let's say, y. So this will be mutual information uncertainty in x minus uncertainty in x given y. Okay, so I wrote it this particular way. Now what is this? We have just seen using chain rule, this can be written in terms of conditional, and similarly this also I can write in terms of conditional, right? Uncertainty in like x1, x2, x3 given y, I can write as uncertainty in x1 given y plus uncertainty in x2 given x1 y, plus I can expand it in similar way. Like I expanded this, I can similarly expand this. So, and then when you combine these two, you essentially get mutual information in the chain rule form. Okay. This may be looking a little clumsy to you that how this is, but this is exactly the same idea. If I ask you to write uncertainty of A, B given C, how will you write uncertainty of A given C plus uncertainty of B given A and C, right? And similarly there is also chain rule for divergence. So if you want to write divergence between this joint distribution P of xy and Q of xy, this can be written in terms of divergence of Px and Qx and this conditional distribution. So again, from the definition, divergence between this P and Q can be written in this particular way. Now I write this in terms of, so P of joint distribution of P of x can be written as Q of P of x into P of y given x. Similarly, Q of xy joint distribution can be written as Q of x into Q of y given x. Now just consider this ratio of Px and Qx as A and this is as B. So log of AB is log of A plus log of B. So this will be log of A and this is log of B. Now this quantity does not depend on y. So when you sum over y, this will become P of x. So this is P of x log P of x Q of x, and then this is expectation of this. This is given by this. Okay. So in a nutshell, basically, I mean, I just wanted to. There are few things I just wanted to specially mention. What is entropy? What is mutual information? And then effect of conditioning. What happens if you condition over another random variable? These results are important. This you will see basically, and how do we quantify information using entropy? That's also important, and you will see in one of the proofs which Uday is going to do on regenerative codes, this trade-off, repair bandwidth and storage trade-off. The same thing which he showed using information flow graph ideas, he can prove the same thing using information theory ideas too. Okay. So with this, I will stop here.